Okay, so this is a question on forced oscillations, and it's actually a real-world example, or at least it's a theoretical simplification of a real-world mechanics example. In this case, what it's analyzing is it's analyzing a wheel inside the suspension system of a car. More specifically, it's looking at this unbalanced weight in the rim of the wheel. Now, if you're driving a car with an unbalanced weight on the rim of your wheel, if you go beyond a certain speed, you'll actually notice that the wheel starts to judder. It starts to vibrate, and you can actually feel that in your steering column. Now, the question basically asks you a similar question to this. It's asking you, what speed, v, does the entire car need to move at for this unbalanced weight to essentially cause the wheel to hop off the ground? So the person who designed this question modeled the suspension system of the car as a spring, and also modeled the rubber in the tire as a spring as well. And both of these have different spring constants. The spring constant of the suspension system is basically going to be equal to its total force on the suspension system, which is the weight of the portion of the car that's above the wheel, and that's W1, divided by its static deflection, which is the amount by which it gets compressed as soon as this weight is added on top of it. The same goes for the spring constant of the tire. So in this case, it's going to be equal to the total force that's acting on this tire, which is going to be equal to the weight of the portion of the car above the wheel, plus the weight of the actual wheel itself, divided by the static deflection of the actual rubber in the tire. By making these simplifications, can we figure out what speed the entire car needs to travel at in order for the wheel to actually start to hop? So before we get started and look at the oscillation of the center of the wheel, let's figure out what frequency, how the frequency of the unbalanced weight going around the rim of the tire relates to the speed of the actual car. In order to do this, we need to assume that the wheel isn't actually going to slip, which is pretty reasonable to assume if the car is driving on reasonable road conditions. If the tire doesn't slip as it rolls, then the entire car should travel the same amount of distance as the circumference of the tire. So that allows us to basically write that v is going to be equal to the circumference of the tire divided by the time it takes for it to do one entire revolution. Now 2 pi over t can also be written as the angular frequency of this unbalanced weight. So that's going to be equal to omega times r. So this allows us to relate the angular frequency of this unbalanced weight to the velocity of the actual car. So we can write omega equals v divided by r. The reason I want to figure out the angular frequency of this unbalanced weight is because I'm going to basically analyze what's going to be happening to the center of this wheel as it's acted on by a periodic driving force. In this case, the periodic driving force that's going to be acting on this oscillator, which is the center of the wheel, is going to be basically the unbalanced weight on the edge of the tire. So that's why I wanted to figure out what the angular frequency is of the unbalanced weight. Now we can figure out what the natural frequency is of the center of the wheel as well. If I imagine nudging the center of the wheel slightly downwards in the negative y direction, then the rubber in the tire is going to compress slightly, and the suspension system is also going to extend by the same amount. Therefore, the effective spring constant that's acting on the center of the wheel, so K effective, is basically equal to the sum of the two spring constants. The spring is going to be equal to the sum of the suspension system spring constant and the plus the stiffness of the rubber in the tire. So it's going to be equal to K plus small k over here. That allows me to define a natural frequency for the center of the wheel. So I'm going to call the natural frequency omega naught. Now, if you've done a bit of reading into simple harmonic motion, you'll know that that omega naught is basically going to be equal to the effective spring constant of the system divided by the mass of the thing that's doing the oscillating. So it's going to be equal to K effective divided by M. And I'm basically saying M is the mass of the mass of the wheel. So in this case, it's going to be equal to square root of K plus small k divided by M. You can also figure this expression out by solving the differential equation for the simple harmonic oscillator, but I think that's a bit overkill, especially because we're going to be doing it including the periodic driving force. So now I've got the natural frequency of the oscillator and I've got the frequency of the periodic driving force. I need to think carefully about what the amplitude of the oscillator needs to be in order for the entire wheel to hop off the ground. So, in order for the entire wheel to hop off the ground, we need to start thinking more carefully about the static deflections of each of these springs over here. So, the static deflections were used to define the actual spring constant, but it actually turns out that if the amplitude of this wheel is greater than the static deflection of the suspension system, then it's essentially going to cause the entire wheel to move up and off the ground. So the criteria I'm going to put for the wheel hopping off the ground is that the amplitude A is greater than delta 1, which is the static deflection of the suspension system. And let's see where this takes it. And now I basically want to figure out what A is in terms of the angular frequency of the periodic driving force of the weight, of the unbalanced weight, and the natural frequency of this simple harmonic oscillator. So in order to do that, I need to make a differential equation. So that's basically going to be using Newton's second law, right? So you have to do it. So Newton's second law is that the net force on an object is equal to its mass times its acceleration. So in this case, the accelerating is going to be happening in the vertical y direction. And that's going to be equal to two forces. It's going to be equal to minus K effective times y. And this is basically the effective spring constant of the suspension system and the rubber in the tire if I nudge the center of the wheel down by a tiny amount, y. So this is basically the restoring force caused by both of these springs. And it's also going to be equal to the periodic driving force F0. But because it's periodic, I can basically, it has to be a sinusoidal signal. So it's going to be something like F0 cos omega t, where omega is basically what we figured out earlier. Now, we can also figure out what F0 is in this case. In this case, F0 is basically going to be equal to W3, right? Because W3 is going to be causing the entire mass spring system to compress downwards a little bit, and it's basically going to drive it every time it goes over the vertical position. So F0 is equal to W3. So I've got minus K effective times y plus W3 cos omega t. Now I can take the mass over to the other side. So I basically get this as the differential equation. I get minus K effective divided by M times y plus W3 over M cos omega t. Now I want to collect all the y terms onto one side so it starts to look like a nicer differential equation. So I've got the acceleration plus K effective over M times y equals W3 over M cos omega t. Now, as we defined this earlier, K effective over M is basically going to be equal to omega naught squared. So this is going to be equal to d squared y over dt squared plus omega naught squared equals W3 over M cos omega t. So at this point, this is an inhomogeneous differential equation because it's not got a zero on this side. It's got some kind of function that's dependent on t. In this case, it's actually a nice function because it's oscillatory, so it oscillates around. that makes it a very nice function to deal with because it means we can basically guess what our solution is going to be. Whatever our solution for y is going to be, it's going to basically also be a function that oscillates around, right? So we can basically use a complex exponential to define our guess for y. So this bit over here, I can also express that in terms of complex exponentials as well. W3 cos omega t, W3 cos omega t is basically the real part of a complex exponential that has a magnitude of W3, and it has essentially a complex phase of e to the I omega t. So if you take the real part of this complex number over here, you're basically going to get W3 cos omega t. Similarly, we can also define our guess for y in a similar way. Y is going to be equal to the real part of whatever the magnitude y naught is times e to the I omega t. So this is basically a loose way of doing the Fourier transform of both sides. So if you're familiar with what a Fourier transform is, you could also do that and you'll basically get the same thing I'm going to get by doing all of this stuff over here. So let me just make more room for this by using another sheet of paper. Let's plug both of these guesses back into our differential equation and see what we get. Okay, so let me just go and plug both of these. Let me just plug the complex exponentials back into the differential equation. So the differential equation, just to reiterate, was d squared y over dt squared plus omega naught squared y equals omega 3 over m cos omega t. But if I'm using complex exponentials, this bit just becomes the real part of a complex exponential. So this is going to be equal to d squared y over dt squared plus omega naught squared equals w3 e to the I omega t divided by m. So if I just remember to take the real part of both sides at the end, then I'll basically get the solution I want, because the imaginary part isn't useful for us, because we're only interested in the cos component. Similarly, I can plug in the y complex exponentials. So I'm basically defining y. I'm basically going to guess that the solution to y is going to be the real part of a complex exponential with magnitude y naught and a complex phase of e to the I omega t. So if I plug this into my differential equation, double differentiating this complex exponential, I basically get minus omega squared y naught e to the I omega t plus omega naught squared times y naught e to the I omega t equals w3 over m e to the I omega t. At this point, I can basically cancel all of the e to the I omega t's. So all the exponentials go, and I'm basically left with y naught times omega naught squared minus omega squared equals w3 over m. So y naught, which is the amplitude of the oscillation, is equal to w3 over m times omega naught squared minus omega squared. So the reason we wanted to figure out this amplitude is because if the amplitude is actually greater than the static deflection, that means the entire wheel is going to hop off the ground. That means the minimum value I can have for this amplitude of the oscillation has to be equal to the static deflection delta 1. So at this point, I can basically put y naught equals delta 1 for the wheel to hop off the ground. So delta 1 equals w3 over m omega naught squared minus omega squared. So if I rearrange this, I want to get what omega is so I can figure out what the velocity of the entire car is going to be. So let's just do a bit of quick rearranging. from omega, we can get what the velocity is going to be. The velocity of the entire car is going to be equal to, it's basically going to be equal to omega times r, because that's what we figured out right at the very start. So it's going to be equal to r times square root of omega naught squared minus w3 over m delta 1. So that's the expression I got for the velocity the car needs to travel at in order for the wheels to actually hop off the ground. So using all of that data you got at the start, I calculated the velocity to be 20.8 meters per second. So the data we were given in the question were like typical values for all of the parameters, and that gives you something like 20.8 meters per second. But the data was also given in gross imperial units. So if you convert all of this to miles per hour, you end up getting around 46.6 miles per hour, which actually ends up being the answer. So it was a super gratifying problem to work on because it combines loads of bits of physical intuition, and it's also a really neat example of how resonance can cause annoying effects in the real world.